let's state the critical numbers, not necessarily the critical points. The points would be a coordinate if we want to get technical. And tell the intervals on which the function is increasing or decreasing. It won't be increasing and decreasing, but it's one or the other. So here we go. Let's do example 1, and that says f of x equals x squared minus 14x plus 2. And let's just think about this one logically, okay? If we were to graph this, then we would have a parabola that opens up. So we know that we're going to have something that looks kind of like this, right? And so whatever we do, it's going to be negative infinity to something, and that's going to be where it's decreasing, and that same something to infinity, and then that's going to be where it's increasing. We kind of know that just by looking at the shape. And if you want to get technical, we could go old school on it and use negative b over 2a, which comes from calculus, not part of this video, but it's really cool. We could use negative b over 2a to figure out where that vertex is, but let's not. In a way, we kind of are by what we're doing. But we're going to find critical numbers. Critical numbers occur where the derivative equals 0 or where the derivative doesn't exist, and this derivative exists everywhere. This is continuous, and it is differentiable everywhere. So f prime of x is equal to 2x minus 14, and that is equal to 0. X equals 7. 7 is the x value of the vertex. By the way, this is negative b over 2a. If you want to really go old school on it, it's just one of those cool things. So x is equal to 7. And here's what we're going to do. We're going to do this thing called sign analysis. And even though you know the shape of this parabola, this is going to come in handy on some other ones. So I'm going to draw a number line. Not all math teachers do it this way, but this is how I do it. So here's infinity. Can't count that far. Here's negative infinity. Can't count back that far. And here's 7 in there. You don't have to put other numbers. Not necessary. So 7 is where this thing turns around. So is it increasing? Is it decreasing? What's it doing and where is it doing it? So here's what we're going to find out. I want to know where it's increasing and where it's decreasing. So we'll switch colors here. And I'm going to pick any number in this interval. Any number. I'm going to pick a number that's somewhat easy to deal with. 10 works. You can use 8. Don't use like 7.293. Don't go there. But I'm going to just pick a number in this interval like 10. Okay? So 10 is in there. And I'm going to find out what f prime of 10 is. Okay, so if I know f prime of 10, then I will have the sign of f prime of 10. I'll know if it's positive or if it's negative. If the slope is positive, then I know it's increasing. If the slope is negative, then I know it's decreasing. So I'm going to find out what f prime of 10 is. We can do this in our head. You plug a 10 in here, you have 20. 20 minus 14 is going to give me positive 6. I could write down a 6 if I wanted to. I don't care. But I do know it's positive, which tells me that on the interval from 7 to infinity, this thing is increasing. Because it does not matter what number I plug in this interval, it's always going to be increasing. Always going to have a positive slope. It won't always be positive 6, but it's always going to be positive. Let's come over here and let's pick a number in this interval that's easy to deal with. 0 is almost always the best bet. 0 goes there. 2 times 0 minus 14. That is negative 14. I don't care that it's negative 14. I care that it's negative 14. Here's my final answer. We have found the critical numbers. We stated it. There it is. And tell the intervals on which the function is increasing and decreasing. So we're going to come over here and go, well, you know what? This function is increasing on the interval from 7 to infinity. We can get into all kinds of arguments about what exactly is happening at 7. Personal opinion, I feel like it's neither increasing nor decreasing. Some teachers use brackets on that 7. I don't think it's really going to matter either way. I'm a parenthesis kind of person when it comes to that. It's open to interpretation. Open, and get it, open interval. Okay. Decreasing. It is decreasing from negative infinity to 7. Again, some people will put a bracket on that 7, which to me frustrates me because I feel like it would be decreasing at 7. It's not, but that's just my opinion. Anyway, nevertheless, that is the answer. It is decreasing from negative infinity to 7, increasing from 7 to infinity. One more time, here's the graph of it. It goes like that. There's your 7 right there. Decreasing, then increasing. Okay, let's go to example 2. Example 2, switching to blue, that rhymed. Example 2 says f of x equals x cubed plus 3 halves x squared. Okay, if you are able to draw this without using a calculator, it's good for you. I'll go ahead and tell you what it looks like. It's cubic, and because this is an odd degree, that means that the ends are going to go in different directions. And because that's a positive 1 leading coefficient, then I know it's going to go like this. So I'll go ahead and tell you the answer, not the final answer, but the answer-ish, is it's going to be increasing, then decreasing, then increasing. But let's suppose you don't know that. So let's kind of go through that process. And we're going to take the derivative, set the derivative equal to 0, solve it, plug some numbers in, do a little bit of sign analysis here. So the derivative is 3x squared plus 3x, and that's equal to 0. And we'll solve it, so we will factor out a 3x. You could divide the whole thing by 3 if you wanted. You'd also have x plus 1. So x equals 0 and x equals negative 1. We have two critical numbers. We have stated them both. So x equals 0, x equals negative 1. So let's do a little sign analysis here. Here's negative infinity. Here's positive infinity. Put them in order. Please don't mix them up. They're written differently here, but the correct order is negative 1 and 0. So let's plug a number in. We can't plug 0 in, right? If we plug 0 into the derivative, not the original, if we plug 0 into the derivative, then we are going to end up with, well, 0. Because that's where we got it from in the first place. So let's plug a number in somewhere in this interval. You don't have to go in any particular order. I'm going to use 10 because I just like to use 10. So 3 times 10 squared, so 300 plus 3 times 10, so 330. Positive 330. Boom. Just to kind of show my work and kind of show that I'm not randomly putting a plus, I'm going to go f prime of 10. Okay. I know this is decreasing based on the way it goes, but if we're going to do it, we're going to do it in our head. It won't take long. F prime of not much to pick from in here. Actually, there's an infinite number of things to pick from, but if you're looking for something easy, pickings are slim. I'm going to go with negative 1/2. Okay, so doing this without a calculator, but that's okay. You can do this. Negative 1/2 gets squared, becomes positive, and that's a fourth. So we have 3/4. Here we go, 3/4. And then plus 3 times negative 1/2. So basically minus 3/2. And so we look at that and we say 3/4 minus 3/2. Well, that's 0.75. That's 1.5. So we're subtracting. We end up with a negative right there. Okay? And then we'll do this one. We'll plug in negative 100. When you plug in negative 100, you have 300 minus 30, still positive. Boom. There we go. Final answer. By the way, I just plugged in negative 10 right there. So final answer is going to be where I actually state the intervals on where it's increasing and decreasing, which we kind of knew from this general shape, a little bit of algebra 2, kind of a math 3 thing. That is where x equals negative 1. That's where x equals 0. Let's write it down. It is increasing on a couple intervals. It's increasing from negative infinity to negative 1. Union, meaning we're going to join two intervals together. 0 to infinity. Technically, that symbol means or. So basically, they're saying if you're trying to find some x value where it's increasing, you can choose from this interval or you could choose from that interval. That's what it really means. And would be if the intervals overlapped, but that's a different story altogether. Negative 1 to 0. There we go. Okay, let's keep going with some of these examples. They start to get a little bit wacky, or actually somewhat simple. When we get to number 4, it's kind of simple. Number 3 is going to be a little bit crazy, and I probably should restrict the domain, but I'm not. I don't feel like it, so I'm not going to. Let's not restrict the domain. If you graph this one, you'll see what happens. It actually kind of goes like this. So it is sinusoidal. It's, well, cosinusoidal, if that's even a thing. But it does like this, but it kind of increases as it goes. So it is 1/2 x plus cosine x. Okay. So what we're going to do is take the derivative and set it equal to 0. I may end up halfway through this problem restricting the domain just because I should have done that in the first place. So 1/2. Derivative of cosine is negative sine, so negative sine x. And then we'll set that equal to 0. So 1/2 equals sine x. And I need everywhere that sine is 1/2. Okay? You know what? I'm not going to restrict the domain. Let's just go with it. everywhere that sine is 1/2. So this is what's happening in our heads right now, right? I hope this is happening in your head. Cosine starts with 1, square root 3 over 2, square root 2 over 2, 1/2, and 0. Sine comes back with 1, square root 3 over 2, square root 2 over 2, 1/2. All right, pi over 6 is one of my answers. So x equals pi over 6. I also need the other place where where sine is 1/2, and that actually happens here, and that is at 5 pi over 6. So there are my two answers. But wait, this thing goes on forever. If you were to graph it, it looks like this. It's really kind of cool. It just keeps on going up forever. So these are not my only two answers. They're not. They're not. So let's make the list a little more inclusive, shall we? Okay. We could go all the way around this circle and reach 2 pi. And then add another pi over 6. 2 pi plus pi over 6. 2 pi plus pi over 6. Common denominator would be 6. And then if I had to multiply the denominator here by 6, I'd multiply the numerator by 6. And I have 13 pi over 6. 13 pi over 6. And then 2 pi plus 5 pi over 6 is going to give me 17 pi over 6. And if you want to get technical, you could go back the other way too. And that would be negative 7 pi over 6, negative 11 pi over 6. And so it's going to go forever in this direction, forever in this direction. And we don't have enough time or hours in the day to figure out what's happening. You already know the general shape, because you kind of know what that is, and that just tilts it up a little bit. And so we're going to do a sign analysis on this one. And we're not going to put too many of them. It's just not worth the trouble. And when we put our final answer, we would have an infinite number of them. And so I'm just going to put some dots and be like, look, it goes on forever in both directions. Okay? So let's put 3 or 4. I'm just going to put these 4. Okay? So pi over 6. 5 pi over 6, 13 pi over 6, these are not spaced correctly, but that's okay, 17 pi over 6, and infinity here, negative infinity here. There are a lot more that are taking place. It keeps going in both directions, okay? So what we're going to do is figure out where it's increasing, where it's decreasing. We're going to find the pattern and stick with it. Okay, this is not a formal proof, but this is just noticing a pattern. All right, so if I plugged in these numbers into the derivative, I get 0. That's the point. Okay, so if you plugged in pi over 6, sine of pi over 6 is 1/2, 1/2 minus 1/2, 0. Yeah, fine. But I'm going to plug numbers in this interval into the derivative to find the sign of the derivative. When I know the sign of the derivative, I'll know if it's increasing or decreasing. Or if I get a 0, then I know it's neither. But that won't happen because this is where it equals 0. Okay, so let's pick a number in this interval, a number between pi over 6 and 5 pi over 6, and if you're looking for an easy one, let's go with pi over 2. If I plug the pi over 2, f prime of pi over 2, let's plug it in right there. Sine of pi over 2 is 1. 1/2 minus 1 is negative. Stop right there. It's negative. That's all I care about. Okay? Let's plug in a number between 5 pi over 6 and 13 pi over 6. 2 pi works. If you plug in a 2 pi here, sine of 2 pi is 0. 1/2 minus 0 is positive. Okay? That was f prime of 2 pi. All right? Let's plug in a number here. Somewhere between 13 pi over 6 and 17 pi over 6, and put that one. So that would be pi over 2, 2, 3, 4, 5 pi over 2. F prime of 5 pi over 2 is the same thing as this. It's negative, and then it's positive, and then it's negative, and then it's positive. And you see the pattern, right? Okay. Now, there are much more formalized ways of writing this. but just for the sake of what we're doing, this was a good one to practice with the unit circle on. Just saying. We're going to say that it is increasing on multiple intervals. This is probably not the textbook way of writing it, but just for our purposes, it's going to be the best way to kind of get this point across. So I'm going to use a couple intervals that I know for sure. So I'm going to say 5 pi over 6 to 13 pi over 6 union 17 pi over 6 to add 12 to that, 25 pi over 6. Keeps going forever in that direction, keeps going forever in that direction. That is not the most formal way of writing it, but we're going to go with it for now. Again, the meat of this problem was understanding the unit circle. I think this is a good problem for that. It is decreasing here and here, so we'll say pi over 6, 5 pi over 6, union, 13 pi over 6 to 17 pi over 6, forever in that direction, forever in that direction. If you want to get a little more technical about it, we could find the pattern here, and we could say, okay, this is a 5 over 6 and a 17 over 6, and the next one would be 12 more than that over 6, and then 12 more than that over 6, and same kind of thing here, 12 more than that, 12 more than that. We would formalize that algebraically. We're going to go with that for now. Okay. That was a hard one. That was a very hard one. If we would have restricted the domain, it would have been a little easier, but we didn't. So, let's do an easy one. The easiest one on the whole paper. It is so easy, you're going to cry. All right. F of x equals negative x. Let's do it. If you were to graph this one, you would realize that it is a line. Example 4. Example 4, f of x equals negative x. You know what? We could just forego all the math altogether. We're still going to do the calculus stuff. But I'm going to jump straight to the answer. It is decreasing. Where? Okay, visualize that line. What is it? It is decreasing everywhere from negative infinity to infinity. Negative infinity to infinity. Because if you were to graph that line, it would go like that. It's never increasing. So you have no intervals of increase. You have just one big interval of decrease, and it's negative infinity to infinity. Let's do it mathematically, right? Calculusically, not a word. F prime of x equals negative 1. We will set that equal to 0. That is a false statement. Negative 1 does not equal 0. So we need to cross that out, and we need to make sure that we're not saying something that is wrong. That is not true. Negative 1 does not equal 0, so we have to put the slash through it. So, if we were to do this, we have negative infinity to infinity. I don't put any numbers in there, because I don't have any numbers to put. I would love to solve for x. There is no x. You don't put anything. So then, if I pick any number in this interval, 0, and I plug it in, where are you going to plug it? Doesn't matter what you do, you're going to get a negative 1. See, you're going to get a negative. This thing is always decreasing. And that's how you would do that if it's linear. You could just visualize it, though. Just say it. Okay, wow, that one was much easier than this one. Good to have a little contrast. Okay, example 5, 6, 7, and 8. Now they get crazy. I thought this one was crazy. We're going to do some piecewise stuff. I just realized this was example 3, but I still had a 1 there. I had all this math right, but I miscounted the example number. Oh well. Okay, example 5. There, turned it to a 5. It's a piecewise function. F of x equals 4 minus x squared, where x is less than or equal to 2, and x minus 2, where x is greater than 2. Okay. I need to know what my critical numbers are. My critical numbers occur where the derivative equals 0 or where my derivative doesn't exist. I wonder if my derivative exists at 2. Okay, let's back up a little bit here. If this graph has a discontinuity, then that discontinuity occurs at 2. All right, so let's do some stuff in our head real quick. Let's set this aside and let's think about continuity for a second. Because there is a good chance that this graph looks like that. It might, I might be way off, maybe down here, but maybe it looks like that, and they do meet up. And not only would they meet up, but the slope at that point coming from the right would equal the slope at that same point coming from the left, and then it would be differentiable at that point. Okay, so we need to kind of keep that in mind. Let's make sure that they meet up, though. Let's make sure it's continuous. So if I plug a 2 here, 4 minus 2 squared is 0. Yay. 2 here, 2 minus 2, still 0. Yay. Okay, great. We have just determined that if we were to graph this, then we would have one continuous piece. Now here's the catch. If the slopes are the same when they meet up, then I don't have a critical number at 2. Okay? Critical numbers occur where the derivative equals 0 or where the derivative doesn't exist. It is continuous, but now I need to know if the derivative exists at 2. If it's differentiable at 2, that means that the derivative of the top is equal to the derivative of the bottom where x equals 2. All right, let's plug a 2 in. Negative 2 times 2 gives me negative 4. 1 is 1. They do not match up. That means this. If you were to graph it, although you would never have to lift your pen, you'd have a jagged, sharp edge right there, and that specific point, which is x equals 2, is going to be a point where it is continuous but not differentiable. Therefore, x equals 2 is a critical point. Okay? So, I'm going to go ahead and write that down. I'm going to keep it in mind because I don't want to forget it. So, x equals 2 is a critical point. Critical number, critical point. You can argue about the specific way to word it. X equals 2 is a critical number. Okay. One more thing, though, we need to do. We need to take the derivative and set it equal to 0. So we still have that 2x equals 0. And so x equals 0. Like, stop, think for a second. X equals 0. Is that in the interval from which we took it? Yes, it is. X equals 0 is a critical number. I'm just writing down what's going through my head. Is a critical number. Okay? Now, the next part. The derivative of that is 1. 1 equals 0. Oh wait, no it doesn't. I don't get a critical number from this portion. Okay? So, here goes. Here's what's about to happen. I just erased all my work and I forgot my critical numbers. I'm kidding. They were 0 and 2. So we're going to make a little number line. It goes from negative infinity to infinity. 0 and 2. We're going to plug numbers into the derivative. Okay? Now, let's do the easy part first. Let's just think logically. That's a line. It has a positive slope. Its slope is 1. From 2 to infinity, if you were to graph it, it looks like that. Vertical line, not vertical line, a diagonal line with a positive slope. Boom. F of anything, f prime of anything greater than 2, it doesn't matter. F prime of 10 is going to be positive 1, because the derivative is 1, right? It's positive. Okay, there's the easy part. You can figure out the rest of it because you know what that looks like, and it stops at 2 right there. So it's going to be decreasing then increasing, but let's do it algebraically just to kind of make sure we understand it. Okay, f prime of 1. Okay, f prime here is not the same as f prime here. F prime here is 1. F prime here is negative 2x. So negative 2x. So negative 2. That one's negative. We're talking about two different derivatives here. This is kind of a piecewise derivative. So if I wanted to talk about f prime, you could, and I think I will in a second, write down the derivative of this. If we wanted to find the derivative at negative 1, well, that would be negative 2 times negative 1. This happens in your head. You get a 2. Therefore, it is positive. Just because it's worth saying and to kind of let you know what's happening in my head right now. F prime of x is a piecewise function, and it is 1 for every value greater than 2. It is negative 2x for every value less than, and not equal to 2 because the derivative does not exist at 2. So this is what's happening here. Okay, just wanted you to see that. And at this point we can tell, we can tell what's increasing, what's decreasing. So let's write that down. It is increasing from negative infinity to 0, or, you're probably about to say and, but technically if we could choose one or the other interval, if we're choosing from a point, or that interval. So decreasing from 0 to 2. All right, let's do another one. Let's do example 4. I'm kidding, let's not. Let's do example 6, because 6 comes after 5. Ooh, this one's fun. It's kind of like the last one, only funner. F of x is 4 minus x squared, where x is less than or equal to 2. Same, not so bad. All right, negative 1x plus 2, where x is greater than 2. All right, so first of all, is it continuous? Let's find out. Let's find out if it's continuous or not. Let's plug in 2 into both of them. If I plug a 2 in here, I get 0. If I plug a 2 in here, I get 0. It's continuous. Yay. If I drew it, I could draw it without lifting my pen. Now, the question is, at 2, does it go, meaning, does the derivative exist at 2? Is it differentiable? Is it a smooth curve? That's not the best way to word it, but it works for our purposes. So, is it a smooth curve? Let's find out. Here is the deal. Let's go ahead and write down f prime of x. And that would be negative 2x for all the x is less than 2, and negative 1 for all the x is greater than 2. And what we really want to know is what exactly happens at 2. Notice I didn't put an equal sign anywhere. So if I plug a 2 in here, I get negative 4. If I plug a 2 in here, I can't. I get a negative 1. So negative 4, negative 1, still not differentiable. Still not differentiable at 2. So I know I have a critical number at x equals 2. I'm not going to write it this time, I'm just going to hold it in my head. There's a critical number at x equals 2 because it is not differentiable there. All right. Now I also still have this. Negative 2x equals 0, x equals 0. There we go. We have a critical number that comes from that. So x equals 0, and now I'll write it down. X equals 2. This came from setting the derivative equal to 0. This came from saying, wait a minute, I can't take the derivative at 2. It's not differentiable at that point. This piecewise function, although continuous, is not differentiable. So then we'll put our little number line. 0, 2, infinity, negative infinity. Let's do some things in our head. Write it down with pink. If we plugged a 1 in, right there, we'd have a negative. I just realized I drew the function wrong on the last problem. When I went like this, it's actually this because it's upside down. And it goes like that. Wow, I was not paying attention to the leading coefficient because it wasn't the one in the front. Oh well. Okay, if we plugged like a 3 in here, it doesn't matter what we plug in here, the slope is always negative there. And then we plugged in like a negative 1. Negative 1 goes there, that would give us a positive there. We have 2 consecutive intervals of decrease. So can we combine them into one? No, we cannot. Because we can't talk about whether it's decreasing at 2. It's not even differentiable there. Okay? Now, there might be some people that would argue semantics over that, but I don't believe that we can say that the slope at positive 2 is decreasing. It's not legal to say because the slope doesn't exist there. So it is increasing from negative infinity to 0. It is decreasing from 0 to 2, from 2 to infinity. Okay, I know 2 is the cutoff point, but we're combining them together. Okay, there are a couple more, and they're going to get a little bit tricky. Here goes, number 7. Because 7 comes after 6. Here goes, example 7. Cube root of x squared minus x. Okay. All right. We need to see where this thing exists and where it doesn't. First of all, it does have a domain of all real numbers. So it exists everywhere. Maybe it's differentiable in some places, and in some it's not. We'll find out in a second. Let's take the derivative first. The derivative of this. You know what? Let's do a rewrite before we do a derivative. That's x to the 2/3 minus x. That'll make it easier. Okay, now we'll do a derivative. 2/3 x to the negative 1/3. Whoa! We're about, that's over 3 in it. We're about to send that to the denominator. That gives us some issues about continuity. That gives us issues about where our derivative exists, okay? Bear with me here. So 2/3 cube root of x minus 1. And we will set that equal to 0. So let's just go ahead and solve that. We'll go through that, and then we'll deal with it a little bit later. Set the 1 to the other side, so we have 2 over 3 cube root of x. That's an ugly 3 again. I'm having a hard time with my 3's. And we will cross multiply, so 3 cube root of x times 1 equals 2. We will divide by 3 and then cube it, and that gives us 8 over 27. So x equals 8/27. That is somewhere between 0 and 1. That'll come in handy to know in a minute. However, we have found where the derivative equals 0. Now we have to think about where the derivative doesn't exist. Critical numbers occur where the derivative equals 0 and where the derivative doesn't exist. And the derivative does not exist at 0, at x equals 0, because you'd be dividing by 0. So x equals 8 over 27, yay, great, fantastic. But also, x equals 0. That did not come from solving, but it did come from looking at this and saying, hey, maybe my derivative can't exist somewhere, and I have to keep that in mind. I'm having a hard time holding these pens. There are 3 of them. I'm having a hard time with the number 3. It's weird. All right, so let's do this. Negative infinity to infinity. 0 and 8 over 27. All right, so let's do this. Let's see what happens here. We're going to plug some numbers in. Let's go for the easy one first. 1 is in this interval. If we plugged a 1 in right here, we would have into the derivative. Sometimes people get mixed up. Am I plugging it into the original or the derivative? What do you want to find? I want to know if it's increasing or decreasing. That is a first derivative issue. If I want to know concavity, that's the next lesson, but that'd be the second derivative. If I want to know how high or how low it goes, the derivative won't tell me that. The derivative tells me increasing and decreasing. How high or how low it goes, that gives me the exact value of the function, so plug that into the original. All right, so if you're stuck on, well, where do I plug it in? What do you want to know? I want to know if it's increasing or decreasing. Sounds like the derivative to me. Okay, plug a 1 in to the derivative. If you plug the 1 in here, cube root of 1 is 1. 2 over 3 times 1 minus 1. 2/3 minus 1 is negative. Good? Oops, sorry. Okay, that's a mess in there. Let's avoid it. Let's plug in a negative. Negative 1 goes here. The cube root of negative 1 does exist. It's not imaginary. Well, imaginary numbers exist anyway, but cube root of negative 1 is negative 1. So this is what's happening in my head. There's a negative 1 we plug in here. That gives me a negative 1. 2/3 times negative 1. So negative 2/3 minus 1 is negative. And now we're going to plug in a number here that is somewhere between 0 and 8 over 27. And I'm going to pretend like your calculator has been stolen. And we're going to do this in our head. It's really not going to be that hard. Let's plug a number in here that we can do in our head. And I think we should use a number that is cube rootable. Does that make sense? 1/27 is clearly between 0 and 8/27. And 1/27 has a very clear cube root. Actually going to work out pretty nicely. So what I'm going to do is plug in 1 over 27. It's just a logical thing to do. It's in the interval, and it's cube rootable, because I know I need to cube root it. And just for the record, we plugged in 1, and we also plugged in negative 1. Just saying. Okay, so let's plug in 1 over 27. Hard to do in our head, so here goes. 2 over 3 times the cube root of 1 over 27, and then we'll subtract 1 from that, and we'll see if it's a positive or a negative, because it might be negative, 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 and it's just decreasing in 3 different intervals. So cube root of 1 over 27 is a third, so 2 over 3 times 1/3. 3 times a third is 1, or minus 1. So 3's cancel, 2 over 1, 2 minus 1 is 1. It is positive. Okay, that tells me a lot. That tells me that is increasing from 0 to 8 over 27. It tells me it's decreasing from negative infinity to 0, and, or from 0 to infinity. By the way, one of the things that I'm kind of doing as I do this, and it's going to come in handy on the next problem, is I'm making sure that the domain is right. Like the domain of this one was all real numbers. So I do go from negative infinity to infinity. It jumps along the way, but I'm going from negative infinity to infinity. The domain of this is all real numbers. So negative infinity to infinity. We're dealing with everything. When we get to the next one, we might have a little bit of a problem. Okay? So here goes number 8. I'm going to put it in a separate video.